Bonjour. Good morning. For today's video, we're going to take a look at a Hall Effect Sensor, an Allegro part number 3144. Currently, it's discontinued. There are replacements available, but there's plenty of them out there, and this particular unit works really well. So hopefully, if you're thinking about a little Hall Effect, maybe snag one up before they go away. We're going to start by taking a look at the data sheet on this sensor. Now, if you're not familiar with what a Hall Effect sensor is, it is a small sensor, well, they can be large too, that can sense the presence of a magnet. So it's a switch that is activated or deactivated with a magnet. So it's non-contact. And that makes them really handy for certain applications. And I do have a project coming up where this is going to be very handy. So here in the data sheet, I've highlighted a few things that are kind of important to know. The device runs at from voltages of 4.5 to 24 volts, which isn't really a concern because this is an open collector. And that can sink up to 25 milliamps. So this can actually be used to drive a small device like an LED or something like that. For application with a Pico, meaning that it's open collector, we're not concerned about the voltage of the device because open collector means it's just providing us with a path to ground. And we'll never see the 5 volt or 24 volts on our side. It's small, commercially available, and it is activated with commercially available small magnets as well. In fact, I don't know if you'll be able to see that. That is a magnet on the end of a screwdriver that I'm using to test this thing. You will need to know the location of the pins, and most importantly, the shape of the device and which side this is viewed from. That'll make more sense in a minute. Come down. Supply current, 4.4 milliamps. Rise time, fall time, it's very fast at less than a microsecond. So it's a very fast response time. Which is important for certain applications. Now here's where you start to get the idea of the shape of the device. And we're going to come down a little further because this one here is the package that I have that I'm using. And it's got tapered edges here and here. The part number is on this side of the device, and that is also the side of the device that you present the magnet to. And then looking at this face, in this view, left pin is 1, second pin is 2, and third pin in order is 3. Now it's important to note so that you can wire the thing up based on pins 1, 2, 3, which if we go back up, here, supply voltage on 1, ground on 0, and then your open collector output is on pin 3. So that's kind of the bulk of what we need off of the data sheet. Now what we'll do is we'll take a look at this in a circuit without a Pico. And I've got it set up here on a breadboard, both in the real world over here and on the breadboard shown in fritzing. In this schematic, what we're showing is 5 volt circuit, 5 volts on the positive rail, 0 volts on the negative rail. The A3144 sensor, the way I had to do it in fritzing, the shape of the device is backwards. The curved side should be on this side with the part number. But if you're paying attention to the part number, this would be pin 1, pin 2, pin 3, based on where you see the part number. We would provide 5 volts on pin 1, ground or 0 volts on pin 2, And then in this case, our output we're going to use to turn on and off an LED. Now the LED, we've got 5 volts coming into that. I'm providing 220 ohms of resistance going through the long leg of the LED. The ground side of the LED is going through a jumper wire into our open collector input. And this will give you an idea of not only how open collectors work, but also how the device works. So let's go right to the breadboard on the bench. Now, over here, I've got my 5-volt power supply connected to it. This happens to be a modular version, or a version of the sensor on a module, which has a tiny LED to show you state, with a resistor here, and then a header for easy breadboarding or use in a project of yours. Now I'm just going to take my little magnet and get it close to the sensor. And in this particular case, the letter side of that sensor is down. So I'm presenting the magnet to that side. Now if I present the wrong pole, the sensor won't go on. But if I present the correct pole, the sensor will activate. And as you can see, the LED here is toggling on and off, and also the one on the module. So that's how versatile this little device is. It can work directly to control a circuit, or in our case, where we would typically use it as a switch or a magnet-activated switch inside of a project with the Pico. So let's turn our attention to that. I'll move this guy out of the way, turn that power supply off, and we'll call up that fritzing diagram. All right. Now, again, very simple. The shape of the 3144 is backwards to the way it's shown here in fritzing. Curved side would be toward the front, and the part number would be on this side. So that means this is pin 1. We're getting 5 volts into that, and that's coming from the Pico. Here's the VSys output. That gives us 5 volts. We're getting ground from a ground pin on the Pico along the ground rail and into pin number 2. Now, this particular pin, our open collector output, is going straight into pin number 15. You'll notice there's an absence of an external pull-up resistor, so that tells you that we must use the internal pull-up resistor. You could use either or, but the way I'm demonstrating it, we're going to use the internal pull-up resistor. So let's turn our attention back to the real breadboard. Here we'll see our ground wire and then our 5-volt supply coming over to the device. 5 volts coming in on pin 1, ground coming in on pin 2, and our output, open collector outputs, coming around to pin 15 on the Pico. Now, if you can't really see, based on the size of the image on the computer screen, the curved side is this side of the sensor, and over here where I'm pointing with the pen is where the part number is for it, A3144. Now we'll take a look at this in the Thani editor where we can see the MicroPython code. In the program, I just got a basic comment saying what this program is demonstrating. We're going to import the machine library, and from time, we're going to import the sleep function. We need to create, or I actually want to create, we don't need this for the Hall Effect Sensor, but it's an easy way to easily determine the state of the sensor. I'm going to create an output here, or a device here, an output called Hall State, and that will show the state of the sensor, whether it's active or not active. And we're using the onboard LED, which is on pin 25. We're also going to create an object for our Hall Effect Sensor, and that'll be an input. And then when the sensor is near the magnet, the signal is pulled to 0 volts. So keep that in mind because it's going to be an inverse logic that we have to work with. So Hall input will be that object, and that's going to be on pin number 15, GPIO pin 15. And I'm using a pull-up resistor, and according to the data sheet, that's about a 60K ohm pull-up resistor, so you're getting a very tiny 0.05 milliamps of pull-up current on that. Very, very minimal. Typical with most of our MicroPython programs, we're going to go into a endless loop. And then here's where all the work is done, and most of that is actually just telling us what state we're in. We're going to check to see if the Hall input, the sensor, if the value is equal to 1, meaning it is currently being pulled high by the internal resistor, the internal pull-up resistor. So that means if it's pulled high, there's no magnet present. So we'll turn off the onboard LED, and then I'm also printing it down below here on the console. Now, if the Hall input value is equal to 0, the sensor is pulling the signal to 0 volts with the magnet present. So that means it's active, and we're going to turn on the LED and print that it's on. Then we'll just slow down the loop to 3/8 of a second here, or 375 milliseconds, so that we can observe things at a good, comfortable pace. So we'll go ahead and run that. Now, this is the flat side over here. This is the curved side. This is the side where the sensor will activate from. So I'm going to bring the magnet into proximity of the switch, and you'll notice that our LED is toggling on and off. And the distance with this magnet is probably in the neighborhood of about 7 or 8 millimeters, or maybe 300-400 thousandths of an inch. You'll also see here on the screen the reflected state of the Hall Effect Sensor. Now I'm going to flip the magnet around, and we'll present the opposite pole to the sensor. Notice we're not getting our signal at all. So it is polarity sensitive relative to the magnet. Not unexpected. But now I'm going to come from the opposite side of the sensor, and we'll see if we can get a reading on that. And there we are. So if we go to the opposite face and present the opposite pole, that will, in effect, activate the sensor. But I would say for reliability, stick with the correct pole on the correct face, and things will be better. As far as north and south, in truth and in practice, it's better just to test it this way, because looking at the magnet, you never see the north and south markings on it, so you're going to test it first and then adhere it to something, put it in a bracket, glue it to something, etc. But that is, in essence, a Hall Effect Sensor. Now, what would you use a Hall Effect Sensor for? Well, if you need to turn something on and off where they can't touch each other, or something can't touch it, that's a great place for a Hall Effect Sensor. Things that move. If something is going to move past another device where your sensor is, that's in a fixed location, you can see the switch turn on and off when the magnet passes by it. So, for example, perhaps an input from for a tachometer of a shaft that's spinning. Or you want to read the position of something embedded in another device, so you can't actually touch the two together. Hall effect sensors are used, or a variation of them, are used in industry extensively. In the hobby industry, where we play, I've seen them used in a number of things. And as I mentioned at the start of the story, I've got a project coming up where these are going to play a fairly key role if it all works out the way I want it. So with that, I think that'll wrap it up here with the information on the Hall Effect Sensor and how to interface it with not only a Pico, but to use it as a standalone device. That'll wrap it up. Thanks for watching, and I look forward to seeing you in the next video. And if you get a chance, please let others know about this channel and like and subscribe. Thanks again.